So what I will be doing today, I will be trying to give an overview of the work we did within the area of resilient power systems. So we show some quantification methods, some cascading models we developed, some planning models, how to embed resilience within investment planning. And overall, I will try to give a glance basically of the different projects that we worked on. So before we go to that, just a few words about the research center that I come from Cyprus, which is called GEOS Center of Excellence. So GEOS basically, it's not an abbreviation. It was the titan of intelligent acquisitive mind from Greek mythology. So he was the brother of Phoebe. So Phoebe was on problem solving. So we tried to give a nice name to the center. We are now a bit over 200 researchers. The number needs to be updated. I was thinking of doing in the morning and I forgot. And we work basically on many critical infrastructures in the centers, from power energy systems, transportation, communication, health management, and so on. And I'm the academic lead in the center in the area of power and energy systems. So we have a quite big group. I don't supervise all these people, fortunately, in the area of power systems. And we cover a quite extensive areas from distribution grids and transmission grids as well. Over the years, from the funding we got from the European Union, from some research councils in Europe, also we work very closely with all the electricity utilities in Cyprus, including the transmission, distribution system operators, and the regulatory authority of Cyprus. So with the funding we got over the years, we managed to build a quite nice infrastructure, a pilot that we have in our laboratory in Chios. So we have a real-time simulator from OpenRT, which basically simulates what we call this kind of digital twin of the transmission network in Cyprus. Now, digital twin is a catchy word that we use a lot. It's basically a digital representation of the transmission network in Cyprus. So we have power amplifiers, we have field equipment for collecting data, we have a communication protocol in cooperation with a transmission system operator in Cyprus for collecting basically all the data in our lab and doing all sorts of experiments and research. So this is how it looks, the transmission network of Cyprus, and we have in total installed with the support of European funding and also with the authority in Cyprus, 18 PMUs across Cyprus. So we have a very good observability of the system. And actually, when something goes wrong in the system, the TSO comes to our laboratory to get measurements to see what went wrong instead of running their own assessment. And so we have this very nice relationship with the TSO there. And we have a rolling contract with them every year. So whenever they have a problem, whenever they want to research something, they come to us. And we're their number one place, if you like, for work. Now you see that we don't have there the north part of Cyprus, which is the North Republic of Cyprus, which is under control of government or whatever. I want to be careful with my words there. From Turkey, that's political stuff. I want to stay out of it. Yeah, we're researchers. So this is a very nice platform. We're working now on making it available online as well, so you can log in our infrastructure there because we're quite remote in Cyprus. You need to take a couple of planes to get there, except the peak season is summer, which is very nice to visit remote flights. So we're working on making this available remotely, so you can basically log into our system, run the experiments, get data, and do whatever you want. So within this is a sort of control center, so you can go into details on the generation that we have in Cyprus. You can log in and see all sorts of details for the substations. And we also have some real-time monitoring on some distribution networks in order to do this coupling of TSO and DSO there. We also have a couple of pilots. First and foremost, of course, is the University of Cyprus, which is basically a self-autonomous microgrid. So we have PV, we have batteries, where we have full access to the data, not so much on the controllability side, so we cannot manage loads in the university. We're pushing towards that in order to expand our research, basically, capabilities. And we're also working with industry, and we have direct access to a wind and photovoltaic park in somewhere in the hills, and not mountains. Where's Oscar and Matteo? Not mountains, hills, close by Nicosia, where we're hoping to install hydrogen facilities there as well to do a sort of hybrid renewable park there. And of course, okay, these are just some demonstrations that we have. So we've been working on this topic of power system resilience for some years now. From my PhD, which was in probabilistic system security at the University of Manchester, and then over the years, were successful in getting projects both from UK as well as working internationally with many researchers from Chile, Malaysia, USA, and so on and so forth. They were currently involved in a number of European projects as well, the R22, the H20CYs. We now go starting a new coordination project in not September, Dirk? R22. Yes, there's no copyright there. We checked with the R22 robot. We checked that. Yeah, because the logo is different, the number we write, the way we write it is different. So it was a coordinator decision, not ours. Yeah. And I'm also quite active still in UK, where I spent 12, 13 years of my academic career. And we have some projects there as well as National Grid and Electricity Northwest. So there has been an uptake and a kind of evolution of the application of resilience in power system. This graph here shows how this evolved in terms of number of applications on the topic since 2010, where there was a big explosion of interest in this. And this kind of circling diagram here shows some of the keywords that were identified in this area. So we see that we're moving from traditional optimization methods to more machine learning and more automation as we move to the current being time now. Now, why resilience got this kind of interest? Well, there are many reasons. There have been rapid changes and stress in the energy landscape, including the increasing penetration of renewables, which stresses more and more our infrastructure. There's increasing reliance on reliable and resilient electricity. Also, the dependence between critical infrastructure are getting more and more. So we need to be actually more resilient when it comes to ensuring the security of electricity supply. And of course, our infrastructure exposed to external threats and shocks, what we call these high impact, low probability events. But what is really a high impact, low probability event when it comes to power systems? This event here, this lovely bull that you cannot see perhaps from the resolution of the projector, actually created power outages in UK. So he had an inching bum, if you allow me the language. So he decided, his name is Ron, he decided to scratch his back on a distribution pole. He knocked down the transformer, and there was a power outage for that village for some hours. The bull was fine, no electroshocked, but the villagers were not very happy. So this can be a high impact, low probability event. Now, what we did in the single working group that I'm chairing back in 2018, when we tried to understand what is really a high impact, low probability event across the world, because we're lucky enough to have members from countries around the globe. So we ran a survey, we got about 80 responses. We basically asked them what they're experiencing there. And of course, you can see in this list a lot of, expected things like wildfires, earthquakes, floods, hurricanes, and so on and so forth. But at the same time, there's also a pandemic there. And this was in 2018. So 1/5 of the people responded that the pandemic can be a threat for power systems. Now, as I say there, I don't know if they experienced a pandemic or had an epiphany or back to the future moment. That was in 2018. Nobody in the working group paid attention to that response there. We all went and we saw, okay, a storm, an ice storm, a physical security, floods, all the things we know. We never paid attention to the response on pandemic, which then after a couple of years, we realized that it can happen. Okay, so within the working group, what we did, we reviewed a lot of definitions of what resilience means. They were quite long and quite confusing. So we tried to basically come up with a simple definition for the concept, as it was quite, ambiguous in the literature. So what we did, basically the colleagues from RSC, which Matteo knows very well, they led basically this work. So we defined resilience as the ability to limit the extent, severity, and duration of system degradation following an extreme event. So we hope that this will be a kind of easy term to use, which has been widely applied in projects and by the industry as well, which was very nice to see. Now, when it comes to extreme event, as we said, and we'll come up back to that at the end of the presentation to discuss it, hopefully with you guys as well. So we refer to high impact low probability events, of course. And then SOE defines basically these things as out of range type of contingencies. If you see at the guidelines of SOE, and they published recently this methodology for identifying these regional electricity crisis scenarios, they include everything. It's a quite wide list, and it's up to the TSOs to basically come back to SOE with their experiences on what they are experiencing as extreme risks in their operation. And we're currently trying to do this in collaboration with the Cypriot TSO as we speak. We are starting now a project to comply with this requirement from SOE. Now, I don't want to tire you, there's many features that we come up with in definition. And then we also compared it with the concept of reliability. So what it means, how it compares with the well-established concept of reliability. And we define basically a list of distinguished features, if you like, including what conditions are considered, what the performance expected when you are exposed to an ordinary event and when you are exposed to an extreme event. And when it comes to extreme events, within the working group, we actually acknowledged that there will be a performance degradation. The important thing is to maintain a minimum level of operation in order to enable the quick recovery of your system. And one very important thing is the compliance. It's basically the regulatory framework that enables or not enables to this more probabilistic, risk-aware investment planning when it comes to resilience. There are much more details. If you like, I can share the slides in this kind of literature to have a look yourself. Now, within our research, what we did, and also with collaboration with system operators to try to understand better how they quantify things and how they actually use them within their cost-benefit analysis, we try to basically apply this kind of risk metrics that we borrowed pretty much from the finance sector, this kind of value at risk and conditional value at risk. So if you simulate thousands of events, you can get a probability distribution, something like this. So in the y-axis, you have the probability. In the x-axis, you have whatever metric you want to use. In this occasion, it's energy not supplied. So usually what we do, we use the mean value of the metric, the expected energy not served, or the average energy not served. We take that value and we try to comply with that value. We set a threshold, and the regulatory authority says to the network operator, if you are below that threshold, you're fine. If you're above that threshold, then you need to do something or you need to pay a penalty. Now, at the same hand, though, we have this tail risk here, where it's where the high impact low probability events lie. So those events can be quantified by this kind of risk metrics that we have in the tail of this probability distribution. So basically, VAR is the value that you set here in order to define basically this region of the extreme events you want to consider. And the conditional value at risk, in a few words, is basically the average of the extreme events you want to consider in your analysis. So you don't take the average of all the events, but you take the average of your extreme events, and you try to plug those into your decision making. Now, the problem is, if you want to integrate this kind of more average-driven, reliability-driven way with a more tail risk-driven approach when it comes to what we call resilience or tail risk events, it will not fly in your cost-benefit analysis because you cannot spend millions of euros or millions of pounds or dollars for an event that might never happen. So ideally, you find a compromise solution. So basically, you would try to find a portfolio of investments that work both for your day-to-day operation as well as under extreme events. And this is what we're trying to do in our research line. And we're quite successful so far to push this in the agenda of the UK regulator, as well as we present our work in SOE, which they find this kind of concept quite interesting, and they're trying to push more to this more risk-aware operation. How are we doing with time? Just to check. Okay. Now, we have this reliability paradigm, and we have the resilience paradigm. The reliability paradigm is simply put is keeping the lights on at all times, if we can. And we're trying to build the system in a way that it's N-1 or N-2 secure. While on the other hand, on the resilience paradigm, what we're trying to do in our work, we're talking about basically N-K, where K in this occasion can be in the order of tens of assets failing in a very short period of time. And the question is what you do there. So you have the N-1 reliability criteria versus the N-K resilience criteria, if you like. And we're trying to implement and to embed basically this thinking within our analysis in order to basically ensure that we sustain a critical system operation, as we said, in order to enable a quick recovery. Now, as we said, there are limitations in current regulatory standards. This is just an example from Ofgem in UK, where basically Ofgem tightened a bit their performance target of the network operators in the last regulatory framework. So the expectation was about 316 megawatt hours from national grid lost per year, down to 147 megawatt hours per year for Rio 2. And now in Rio 3, which will take place in a couple of years, that number is expected to reduce even more. But this is an average value. This is what we said earlier. So we can see from this graph here that on average, national grid was doing well. But you also have these events that go above the limit, for which basically a national grid expected to give, justification to national grid about their poor performance. Where in reality it's not really poor performance. I mean, they did well. And also had the August 2019 blackout, which goes beyond this kind of ordinary or the average event that national grid might actually experience. And when reviewing data from UK, we did this exercise with my PhD students. So we reviewed a lot of UK outage data as reported from the DNOs. We actually see that indeed weather-related outages is the number one reason for customers, number of customers per power cut, and also the duration of the disconnection of customers. So weather-related events needs to be taken into account in the regulatory frameworks. So the first thing we did some years ago, we tried basically to develop a model, a tool that will help us in-house quantify the impact of different events on the system. So we developed this kind of model that we call resilient. My researchers tried too hard to find words to match that abbreviation. He wanted to call it resilience, so he came up with this long name, which I never learned to say. I just say resilient, which basically what this simulator does. Of course, we first take the network, then we take historical event data, so we can basically train our model to either replicate past events or generate full stochastic events. We also have fragility curves, which I will show later, where basically link the failure probability of an asset with the intensity of the hazard. Then we demonstrate, we develop basically the spatial and temporal movement of the event on the system. We did windstorm, we did earthquake, we did fires, and so on. So we have models for all these sorts of hazards. And then we do the impact analysis, where basically it can give you a demonstration something like this. This is an example we did within the Universal project, where we tested basically the algorithms on a test network in Portugal, where we had a windstorm passing through the system. We can define which lines will trip, which lines will not trip, and then define where you expected to lose some demand. Now, this is how more or less how it works. So we have first the spatial and temporal modeling of the event. So this dot there, of course, is not great in terms of visualization, but that circle moving is a windstorm that moves across the system. Then we take the profile of the event and we plug it into the fragility curves to do this fragility-driven impact assessment. Then we can get the time series of the network status. So we can see as a function of time and space, which lines will trip, when, and how long it will take to restore them, which then pass basically into our impact assessment tools to quantify any metric we want to quantify. This is how a fragility curve looks like. So basically in the y-axis, we have the probability of failure. In the x-axis, we have the hazard intensity. This is just an example of wind speed. But basically, this is characterized by probability functions that you can play with the mean and the standard deviation. And you can also fine-tune these characteristics from real data, historical data, if you have, to better represent the performance of your system. So if we see a simple example, if we have this 4-bus system, we project it to some geographic areas. We simulate an event, which is the dotted lines there. So the simulator can actually identify the intersection point of the event with the network, and can basically take the wind speed that the asset is actually exposed to. We map that to the fragility curve, and we get the failure probability of that asset. And then we can basically decide if that line will trip or not. And at the end, what you get is the time and the hazard-dependent failure probability of the assets you have in your system. And again, that can be because of wind, it can be because of earthquakes, of fires, of floods, and so on. We simulated quite a wide range of hazards within the different projects. This is just an example of UK, where basically, again, this red circle is a storm moving across UK. And with the yellow, basically, it was the lines that were affected. And we can see in a spatial manner as well where National Grid is expected to have some issues. So we did that application within the Forward Resilience Measure project, which was completed a couple of years ago. It was the first project that National Grid actually funded to look into this matter in a bit more detail, because they started getting very concerned with high wind events in combination with floods. And now they are number one risk in UK. You don't believe it, is wildfires. It's wildfires, not because they have a lot of wildfires, but because they're not prepared at all if a wildfire ever happens in UK. Gora makes the joke that we're the most resilient country in the world on wildfires because it never happens. If it happens, it will rain to stop it, So, so within this project, we had a qualitative and quantitative method. So it was a co-creative development progress with stakeholders within the business of National Grid, but also with other network operators in UK. The colleagues from Arup, the consultancy company in UK, they led basically the qualitative study, where they developed this kind of multi-dimensional framework, and then define different number of goals, different number of indicators, in order to quantify the resilience maturity of National Grid in terms of business structure and business continuity, not in terms of the infrastructure, but in the terms of National Grid as an organization. So they did this kind of self-assessment with National Grid to see how mature they are when it comes to dealing with extreme events, identify any bottlenecks and so on in their business structure to be better prepared and do the interventions needed basically to respond to an event. We were responsible, of course, for the infrastructure impact assessment. And we use this network that you see in the slides. Of course, we stayed away from Scotland because that's managed from Scottish Power. So we modeled only the England and Wales system. We simulated all sorts of events, all sorts of wind and flood events across UK. And we got, of course, quite a few results. What was really interesting for National Grid and why we're doing the project, the National Infrastructure Commission in UK published a report calling all network operators to have in place a stress testing approach. So when we say with stress testing, it's basically exposing your system to as many extreme scenarios as possible in order to identify basically the breaking point of the infrastructure. So the intensity, if you like, or the location, or any characteristic of the event that would actually result in reduced performance, reduced reliability and resilience of your system. So we did that exactly in this project for National Grid. So we exposed the system to thousands of events. So every dot you see here basically is a windstorm that we simulated for UK. For National Grid, we actually identified the breaking point being around 38, 39 meters per second in UK. And from historical data, indeed, the breaking point of UK was about 40 to 41 meters per second. So we're quite close from the simulations we did. And National Grid is using now this project and the follow-up project we have with National Grid Wellness to use the proof of concepts with Ofgem in UK in order to pass basically this risk-aware and resilience-oriented planning within the next price incentives in the regulatory framework. So within this wellness project that is going on now, we also include Electricity Northwest in order to do this kind of TSO and DSO coordination in case of emergencies. We also included Imperial College London, Goran Strobak, the Professor Goran Strobak, who is more into modeling into more the flexibility services from distribution networks and also multi-energy systems. We also did similar work in Chile with the Chilean independent system operator there. We had a project with them for 2 years. And we're basically interested in seeing the impact of earthquakes on the system. And because unfortunately, Chile is exposed to some hundreds of earthquakes per year, they had very good data to give us in order to, it was good for us, not good for Chilean people, of course. But we managed to basically build very nice fragility curves that we used in our analysis. And instead of using one fragility curve, mainly for substations, that were the biggest concern, we basically defined a family of fragility curves from minor damage up to the total collapse of the asset. So it's more or less the same approach, which I don't want to go into details. But what we actually did, we simulated hundreds again of earthquakes on the system with different epicenters, different intensity, different pinch intensity, and so on. And we just see here 3 representative examples of those we modeled. So within these simulation models, we can define different metrics. So we can have the metric on the number of islands created, on generation units damaged, on substations, how long it took to repair, and so on and so forth. So this is a direct output of this simulation model. And you can also do different things on criticality assessment on the assets you have. So we're able to identify some critical central nodes in Chile when it comes to being exposed to earthquakes. And the tool we developed, coupled with the planning model, is actually being used from the Chilean independent system operator for their system operation and planning. We also did work on wildfires. So again, driven mainly from the close collaboration we have with Chile. Also in Cyprus, they're very much concerned, of course, for fires. We developed different models to capture basically this kind of spatial and temporal movement of fires across a region. So we have models to basically take into account the probability of ignition, the spatial temporal profile, the severity of the wildfire, and different characteristics coming to the direction, the height, the width of the flame, which are very critical to consider when it comes to fragility assessment. From data that we got from European system operators and Chilean system operators, we're able to build what we call this kind of wildfire fragility curves. So these curves basically are related to the distance of the fire with the transmission tower and line, and the wind speed as well. So how fast it moves and how fast it can basically make the fire worse and more dangerous for the transmission conductors. So similarly with before, we did apply this method in the Concepcion power system in Chile. So it was so the beauty of the models we have, fundamentally, they work for, I don't want to say for any kind of event, but if you have the spatial model of the event, the temporal model, and the related fragility case, you just plug them in the models and you get the impact assessment. Okay, that's a big if, I know. But so when we did here, we basically ran a risk assessment for the Concepcion power system in Chile, which is quite weakly connected to the main system. So you can define the energy no supply, some severity risk indices, and so on, as a function of the number of fires you have in the system, because you will never have only one fire. Unfortunately, we have many fires at the same time, and also for the maximum flame, the maximum height of the flame, which affects the failure probability of the line, as well as the opacity capacity of the line, how much current it can actually transfer. Another application we did was in Sarawak Energy in Borneo Island in Malaysia, where we're most interested looking into floods and landslides and how that affects basically the resilience and sustainability of rural microgrid or rural villages in the Borneo Island in Malaysia. So we basically did this kind of compound hazard modeling for that area. So we came up with flood models, flood maps, sorry, and landslide maps. And we're tasked from Sarawak Energy to actually recommend some ways in order to electrify some remote villages in Malaysia, in Borneo Island. So we had basically 3 kinds of scenarios that we developed with Sarog Energy, we had one on following the existing roads because that's basically easy to do. You just put the distribution poles next to the roads. And then we had scenarios for avoiding a moderate high risk of landslides and moderate high risk of flooding. So when it comes to the easy access scenario, following existing roads, it was fine. I mean, you just build the infrastructure next to the road. But we actually identified that if you do that, you go through an area where you have a quite moderate to high risk of landslides, based on experiences as well. So alternatively, what we recommended based on our modeling, we recommended the red route here, which goes through the jungle, unfortunately, but it has a lower risk of being exposed to this kind of extreme hazards. And this is what they actually did for electrifying this village you see on the top, which I think this doesn't work. The villages you see on the top for electrifying those villages, and that line is now in service for 3 years. So it's still working properly. Yes. Yes. That very much had to do with it. It's not a big transmission line. It's just more distribution line. Yeah, yeah. It's not big towers and stuff. Yeah, yeah. You can create hazard. Yes. So you change the risk map that we created. You change it from your intervention in nature. Yeah, yeah. You can do that. But for 3 years, what happened? There was a landslide somewhere close to this road, which we said don't do it there. For 3 years now, it's fine. So because of COVID, unfortunately, we didn't have the chance to go back to revisit the villages there to get their experiences. But our Malaysian colleagues have been there. They're telling us that the villagers are happy so far. So if they are happy, we're happy, isn't it? Yeah. Okay. So how are we doing with time, Natisha?
Okay. About 5 minutes.
Okay. Okay. I think I will manage. I will speed up a bit at the end as usual. Okay. So what we talked about so far, basically, what we were doing, we're having an outage, we're tripping the assets, and then we're running basically an OPF to get the outputs that we wanted to quantify our different metrics. We didn't consider any cascading analysis and cascading propagation, what we discussed yesterday. I apologize to the guys if you have to hear it again. So we know that when there is an outage, you can have the slow phase of the propagation of the cascading, where basically assets are tripping slower. Usually these are overloads of lines, which if you don't do something quickly, lines will trip. And then you reach a point, as we have here from the example of the 2003 blackout in USA, where you enter the fast cascading phase, the fast phase of your cascading. So you enter, there is a tipping point where basically things start getting worse much faster. And there basically you cannot rely on human intervention. You rely mostly on the automation actions you have in your system. And data show that basically this slow phase is getting smaller and smaller. So basically things are happening much faster. So I mean, most of the cascading and the big events that we see now happen very fast in the order of seconds to minutes. So we need to have this kind of cascading simulators to actually understand how fast they move and how your protection actually operates when there is a big disturbance in your system. So what we did over the last 4 or 5 years, we developed a couple of cascading failure models. This is the first model we developed, which we call the AC cascading failure model. Not much imagination there. ACCFM, which basically is a recursive model. So it can handle the cascades in each island individually, can go into each island and continue the cascading, and don't just stop when you have islands and just black out those islands, as many cascading models do. It's based on AC power flow. It can handle a big set of initiating contingencies. So it's quite stable. It converges quite well. The limitation of this is that it's a static representation of the dynamic performance. It's not full dynamic model. And the reason why we did that is because we wanted to have a faster model. Then we developed a dynamic model, which I will show later, which basically is much, much slower. So this is how it works. It has all sorts of protection mechanisms there for frequency, voltage, and load protections. As we said, it's a recursive model, so it stops only when the cascading stop in each of the individual formed islands in the system. And what you can get this kind of tree-like representation of a cascading. So basically, it can tell you at each of the iterations of the cascading, which protection mechanism operated, by how much it operated. For example, how much load you lost because of your anti-frequency load shedding scheme. And starting from the healthy node on the top, where you see with purple there, you have the event, then you have different protection operation sequence. And then you can see the system splitting basically into different islands. And for each of that island, you can see from the graph that basically the simulator continues running, creating more islands as needed, and blackouting some islands or saving, surviving some of those islands as possible. So this is a very nice visualization that we are using in different projects now as well. And system operators like this kind of graphs because they help them understand what actually happened and during a cascading. Now you can simulate, you can output all sorts of other metrics as well. For example, this is the loss load as a function of the cascade step that you had during your propagation. You can also quantify the impact of increasing load or increasing flexibility in your system when you put more distributed generation in your system to make it more responsive, more flexible. And then bars here, each color of the bars here actually see the percentage of lost load because of each protection mechanism you had in your system. So you can actually understand from this simple exercise if your system more sensitive to frequency issues, voltage issues, and so on, from this kind of analysis. It's also available in GitHub if you go to download and have a look at it. I know from people that used it, it's quite easy to set it up and start running it. But dynamics are increasingly important, as we know, with the increasing penetration of renewables, all the known initial problems we have in modern power systems. So in collaboration with my dear colleague and friend, Robin Price of Manchester, we developed, building on the simulator we shown before, we developed the dynamic cascading fault model. Again, no imagination, DCFM. So basically, this is built in Power Factory. So we're running dynamic static Power Factory. It has synchronous generation modeling, demand, wind, protection, frequency containment, and so on, all embedded within one simulation. So before we go that, so basically, I didn't have in the slides because I think it was going to take too much. So the Power Factory model is basically integrated with Python API and with MATLAB as well in order to automate the scenario generation and to feed directly events to simulate in Power Factory. So it's fully automated. If you want to run N-2 and -3, you just put it there. You wait, of course, for a few hours or days to finish, but it's fully automated. So you can run all sorts of security and dynamic studies you want with the model. So this is just an example where we increase basically the wind penetration in the system. So this is for the 200, I forgot to add it. This is for the 200 bus system from Illinois, the test system that we have. So we kind of quantify this, the impact of renewables using the expected demand not served, also conditional value at risk we discussed earlier, and the value at risk. Of course, the expected demand is the lowest bars you see there, the value at risk at the middle, and the conditional value are the ones on the top. And we compare these metrics with and without FFR, support from the batteries, to see how basically the situation changes when you are increasing the wind penetration and how basically beneficial this fast injection of energy from batteries is when it comes to especially extreme events. And you can do all sorts of other things as well. You can quantify basically your initial levels, your frequency nadir. You see, you can quantify the required battery capacity you want to have to save the system. And we're also experimenting putting the batteries close to the renewables or close to the demand to see the impact of that on the system as well. I think I will skip this. This part is interesting. So what we did here, basically, we all know that you have an increasing cascading and blackout risk in higher demand levels. That has been in the literature, that has been examined quite a lot. So what we did in our analysis, we basically started running these studies from demand levels from as low as 50% or 40%. So what we noticed is there is this bump here at around 50 to 70% of demand, where you actually have a quite increased cascading risk using either as a static model, the first model, or the full dynamic model we shown now. So this which was basically kind of confirmed also from National Grid and other system operators who have in European projects. The reason for this is that when you have big penetration of renewables, or mainly wind, into single points in your system, that part of the system can be quite overutilized. So high winds usually happen during low demand levels, so during night. So when that system is overutilized, if you have a trip at that part of the system, then it's quite easy to propagate across your system. And this is an increasing risk that they're actually considering. So it has this within their scenarios. So what will happen if you have very big injections of wind from offshore, for example, wind generation into a small number of points in your system? What happens if you get a problem in that part of the infrastructure, especially during night? So this is an increasing risk they're considering, and we have sort of results to actually demonstrate that. These simulators, again, available in GitHub in the repository of the student that actually developed the model. So you can actually, again, download it and use it freely if you want. And if you have any issues, guys, it goes by saying, get in touch. We'll be able to be more than happy to help you get up and running. So very briefly about this HVDC WISE project that we're involved now. I said it yesterday as well, I'm not an HVDC expert, just to put it out straight. So our role within this project is to actually implement this kind of cascading models that we have in the AC and DC grids to see basically how and if the HVDC links can act as a firewall to propagate the cascading propagation from one system to another. So this project is led by Supergrid, which is based in Lyon in France. So we basically, it's within the concept of the presentation we discussed today. So we're trying to see the combination of the impact assessment of increasing renewables in the system when being exposed to all these kind of extreme events. And again, we're trying to quantify basically the role of HVDC in maintaining the system security and resilience against extreme events. So we developed this framework within the project. There are many in the project website. There are many deliverables that you can go and read about the literature review, what technologies other colleagues are developing, HVDC technology other colleagues are developing in the consortium for us to use and test in our simulators. So this is a quite flexible simulator that we developed for the project. So the cascading simulators, both what we presented today, the AC, CFM, and then DCFM, are coupled with the event simulator. So the event simulator actually simulates all these kind of extreme events. Then it can plug them in to the cascading models to quantify the cascading propagation. And then the idea is to also try to see how different operational mitigation strategies, for example, control islanding or black start using HVDC, can actually help more the whole system resilience. So, okay, these are just some, we're using basically the expected demand not serving the condition of value or risk as metrics within this project. So we're focusing only on the first phase there, on the cascading propagation, and other colleagues in the project are working on the restoration side to close basically this trapezoid. So we tested this in a very simple test system first, just to see if it works. Currently, we're trying to run it on the real use cases we have in the project. So we just connected 39 bus with a 14 bus system with a point basically VSC HVDC link. And we have there the characteristics for the controllers, the initiating events, and the metrics. And what we did, we exposed this system to all sorts of contingencies coming starting from n-1 contingencies, and this is a probability distribution for the frequency distribution for the outages we considered. So you can see basically that with the right hand side is with the DC link, and the left hand side is connecting the two areas with an AC link. So with an DC link, we actually basically curtail this kind of heavy tail risk, and we move the probability distribution more to the left, so we avoid this kind of big extreme events. The same behavior is observed for n-2 contingencies. So we basically curtail with the HVND ceiling in place the more impactful events. But when it comes to n-3, when things are getting very serious, let's say, the tail of the probability distribution is improved. So we see basically here less extreme events, but the frequency of smaller cascades, smaller basically power cuts is getting higher. We're trying still to understand why this happens, and we try to basically understand this kind of dilemma, if this is preferable or not, when it comes to this kind of implementations and exercises. And we're basically trying to test different HVDC technologies, which are provided from other partners, which is quite difficult for us to actually plug them in their models because, as I said, we're not HVDC experts. So we rely a lot on other people, which I don't particularly like in this project, that part of the project, but it is what it is. So these are the use cases we have in the project. So we have the mainland European system, of course, a simplified version of the system. We have the Great Britain one, and we also have an offshore system within our use cases, and we have all sorts of events and extreme operating conditions to hopefully simulate through our simulators that we have at the University of Cyprus in the project. This I think I will skip because I talk too much. So basically, these are different things you can do with this cascade simulator. So you can do control islanding in order to save the propagation of the cascadings. We also did work on zonal black star restoration. So with the cascade simulators, what we're trying to do, we're trying to limit the amount of demand you can restore at each step in order to maintain the system stability. Because as observed from real restoration plans, when you're trying to energize a line or a generator, when you actually try to break in service, you create more problems, and then you go again into instability. So within this work, what we're trying to do is at each simulation step, before each restoration action, we run the dynamic cascade simulator to see if actually that action will have the desirable output, or if it's going to trigger more cascadings. And this is basically how it looks. So we have the initiating event at the beginning, and then we have the restoration phase slowly. And you see this kind of step restoration because we consider a 5-minute window for each restoration step, which is more what's used more in the literature. I will skip this as well. Is machine learning applications, which are quite interesting, but I want to talk about something else. Okay, so how everything is plugged into planning. This is the last thing I will talk about. So this is a model we developed within the Universal project, which you are involved as well. So we developed basically this kind of integrated optimizer, which was taking into account the fragility-based models that we have. We were simulating thousands of scenarios. We're reducing them if needed to be computationally tractable. And then we developed this optimizer basically, which uses a weighted optimization model in order to try to find a balance between the expected energy not supplied, so looking more into improving your performance on day-to-day operation, with the conditional value at risk when it comes to planning against extreme events. So Vita here basically defines the risk appetite, if you like, of the investor. So if you put Vita equals to 1, so you basically eliminate your expected energy not served. It's like you're focusing only on your conditional values, only on the tail risk events. So you're doing more resilience-driven planning. If you put Vita equals to 0, you basically ignore the extreme events, and you use, as we do currently, the average metrics for your planning. So what we did with the, yes. Uh, yes, we compare the more. So what we do, we apply the event simulator thousands of times. So the event simulator will give you n-1 to n-10 scenarios. So we do that. We have all the database with those contingencies. And then we do an n-1 analysis, which is basically the benchmark reliability. Yes. Yeah. We're starting with that. Yeah. Yes. Yeah. We did that in other papers. Yeah. Because I think I overtalked anyway, so I could have include everything in the presentation. Yeah, but they set the initiated conditions is n-1. In UK, the project we have with National Grid is n-2, which basically constrains a lot what you can do. Which is not in many occasions is not the most economic operation, but they want to do it. We set up the system in the previous project -1, to be too easier for us as well. And they told us off in the first meeting. No, it's n-2. So we went back and did it -2. We constrained it further. So you're running a security constrained OPF there. Yeah. Okay, so a simple illustration for the 33 bus system. So basically what we did within the project, we took the risk neutral approach. So the risk neutral approach is basically considering Vita equal to 0. So we basically expose the network to a lot of events. Then we throw these options in the optimizer. So hardening your overhead system, putting your lines underground, or putting more batteries in the system to make it a bit more flexible. So as expected, when we do the risk neutral approach, your expected energy not served is basically optimized. So you get here your best performance for expected energy not supplied. So there's not much curtailment or much movement, let's say, in the tail. When do we do the risk averse approach? So the risk averse approach refers to basically Vita equals to 1. So you're on the other side of the problem. Your tail events are curtailed. So you're having a better performance on your tail risks. And we see that basically the optimizer decided to underground some lines to make them not vulnerable basically to winds and floods. The compromise solution is something in between. It's something to Vita equals to 0.5 that we used in this demonstration, where you actually get a kind of compromise solution between your expected and your conditional values. Now, the question there is when you present this to system operators, you're like, why should I use Vita equals to 0.5, not 0.6, 0.7, 7.8, or whatever the value is? So what we did are many decision variables. So what we did within the project in collaboration with IREDES, basically we varied your risk averse variable, which is Vita. And then we try to define a different investment portfolio for each Vita value and for different varying budget you have in your for your planning. So we have this kind of 3D plane here. And in this 3D plane, there are many dots which represent different investment portfolios. So the system operator in this way, they can filter basically their risk aversion level that they want with the budget they have available in order to get some recommended investment portfolios that can basically satisfy their risk aversion approach. And we also did this with alpha, which basically alpha defines the tail that you want to consider in your probability distribution. So how many extreme events you want to actually consider. And this kind of works and this kind of visualizations. Okay, I'm not a big fan of 3D figures, but we can plot them in parallel plots, and then you can put your own filters to see which portfolios. These are kind of more acceptable from the system operators because the decision is there. We don't go and we tell them this is the best option, but we offer them this kind of sensitivity studies, if you like, and we let them up to them to decide. So we did similar things for chilling. And this again, the ranking of different investment portfolios when it comes to more reliability-driven operation and resilience-driven operation. In the first option in both the approaches was the HVND ceiling that they built in Chile, were basically to connect the north with the south, which bypasses a lot of the infrastructure that's exposed to earthquakes. The interesting thing here is that when you look into your resilience investments, the optimizer was basically prioritizing hardening the substations as central nodes in the system. And Chile, it's a very long country, so basically it's a radial network, their transmission system. So hardening your substations is actually very much important. And we did this for kind of different budgets. And basically the optimizer was giving a mixture of HVDC technologies, hardening your infrastructure as well as adding some flexibility into your system. I think we're done with time, right? Yeah. Okay, so I will skip this. This is just okay, some for mobile energy resources scheduling stuff. Yes, this was just some slides for the R22 project, which you can see later. And I think I will close it here. Yeah. These are just some open questions that we had. And just to answer the question, if we're ready, the models and the technology, I would say, is there, but we have quite some issues when it comes to operational regulation and also planning regulation. It's the big obstacle that we're facing now in this line of research to actually transfer our models into real application, because we have these barriers basically from the regulatory and policy perspective. Okay, so that's it. And just to advertise our book that is coming hopefully at the end of the year.